So as you know, the pumps are used to increase the energy level of water, by virtue of which it can be raised to a higher level. So this task we can done with the help of dynamic pressure pump. Okay, or by positive displacement pump. So the dynamic pressure pump is the centrifugal pump that we already discussed, and the positive displacement pump is our reciprocating pump. Okay, the working principle of reciprocating pump is altogether different from that of centrifugal pump. So the reciprocating pump that are called as positive displacement pumps also. Now this is because a small quantity of liquid is taken into the chamber and is physically displaced and forced out with pressure by the moving element. Okay, so you can say in this reciprocating pump, the small amount of liquid is taken into a chamber. Okay, and from that chamber, it is pushed forward with the help of some mechanical element. With the help of some mechanical element. So this mechanical element physically pushed that liquid into the chamber to the higher level. Now this mechanical element, it can be a gear system rotating in a housing. It can be a gear system, okay, or it can be a piston cylinder arrangement. Okay, so thus, if we rotate or emptiate that chamber with the help of piston, and further that piston is controlled by some another external element, so that type of pump we call as the reciprocating pump. Okay, so here the chamber is alternately filled with liquid, and that liquid is pumped out with the force of the piston. And again that cylinder, that chamber is filled again, and again that liquid is pushed out with the help of piston, and this cycle is going on, and such type of pump we call as the reciprocating pump. So the volume of liquid that we pushed in case of reciprocating pump will depend upon the speed with which the chamber is filled and emptied. You can say the volume pushed from the chamber is proportional to the speed of the you can say the speed with which the chamber is filled and emptied, and that is further proportional to the speed of the moving element. Okay, so that is our reciprocating pump. But nowadays the use of reciprocating pumps are limited, so that are replaced by the centrifugal pumps. But in industry, in some application, this reciprocating pump is used. So normally these are used in the situations where we have to extract liquid from the deep, and at the outlet we require low discharge. Okay, so for oil extracting, normally we can use, or you can say for oil drilling, we can use reciprocating pumps. The next we see the main components of reciprocating pumps. The main components of reciprocating pump. Now the main components are, so one is the sump. You can see here the sump. Okay, there is suction pipe, there is delivery pipe, There is piston cylinder arrangement. Okay. So there are two valves. One is called delivery valve, and another one is the suction valve. Now the movement of piston is controlled by piston rod, that is further connected to crank with the help of a connecting rod. So these are the main components of a reciprocating pump. So accordingly, we have the heads over here. One is the suction head. You can see it is from sump level to the center of the cylinder, and another one is the delivery head HD, from the center level to the higher point where we have to deliver the liquid. So these are the two heads, and sum of suction head and delivery head, that is called static head. Now here we have two important valves. One is the delivery valve, second one is the suction valve. Now these are the non-return valves. You can say these are the unidirectional valves. In such valves, liquid allows to go along one direction only. So these are the non-return valves or the unidirectional valves. So that is the suction valve and the delivery valve. Now here, the rotating element is our crank. Now this crank rotates from initially 0 degree to 180 degree, that is in clockwise direction. So when this crank rotates from 0 degree to 180 degree, so our piston moves from extreme left to right. Okay, the piston moves from extreme left to right. So during that, my suction valve is open and delivery valve is closed. So my suction valve is open and delivery valve is closed. Okay, so that movement of piston is called the suction stroke. So during this stroke, the water is filled into the cylinder, filled into the chamber. Okay, so in the next, when this crank rotates from 180 degree to another, now say this is up to 360 degree, that is the second half. In that time, my suction valve is closed, delivery valve is open, and this stroke we call as delivery stroke. This is called delivery stroke. So during this, suction valve is closed and delivery valve is open, and piston moves from extreme right towards the left direction. Okay, so during this stroke, the delivery is available, or you can say the liquid is available on delivery pipe. Now these two strokes, suction stroke and delivery stroke, completes the one cycle of reciprocating pump. That completes the one cycle of reciprocating pump. So in one cycle, you can say we have two strokes. Okay, so here we got the water from single side of the piston. You can say this is also a single acting pump. This is a single acting pump, or you can say this is a single acting reciprocating pump. So when I talk about the working of this reciprocating pump, you can see my crank rotates from 0 to 180 degree. There is suction stroke. So water from sump comes into the cylinder, and that time suction valve is open, delivery valve is closed. And when crank rotates from 180 degree to another 180 degrees, that is to 360 degrees, that is my delivery stroke. So at that time, the suction valve is closed and delivery valve is open. So there is discharge available along the delivery pipe. Okay, so that completes the one cycle of the reciprocating pump, and this cycle goes on repeating, and accordingly we got the delivery or the liquid on or during the delivery strokes. Okay, this is how this pump works. The next is the classification of reciprocating pump. So for classification, the first classification is according to the use of piston side. According to the use of piston side. So as you see in this diagram, we are only using the one side of the piston. Okay, so that is called single acting reciprocating pump. So the one type is single acting. Okay, the second type is double acting. Now you can see in this diagram. So here the both sides of the piston are used to deliver the water in the delivery side. So you can see here this side is also used to deliver the water in the delivery pipe, and this side is also used. Okay, so when both sides are used to deliver the water, so that we call as double acting reciprocating pump. Now you can see how this pump works. Okay, so my rotation of crank from 0 degree to 180 degree, you can see. So their piston moves from left to right. Piston moves from left to right. So during that, you can see the water comes from sump and collected over here. Okay, and from this side, the water goes to the top toward the delivery. Okay, so during this stroke, that is on one side we have the suction stroke, of another side of the piston we have the delivery stroke. Now during this, you can see uh, my this suction valve is open. Okay, we have two suction valves. This suction valve is closed. This delivery valve is open, and this delivery valve is closed. Okay, so this is what happens when crank rotates from 0 to 180 degree. Now in the next stroke, when my crank rotates from 180 degree 180 degree to 360 degrees. So at that time, my piston moves from right to left. Okay, this is the direction of piston movement. Okay, so at that time, you can see, so water comes from this side. So here the suction takes place, and water delivers from this side to the delivery pipe. Okay, so at that very time, my this valve is suction valve is open, this suction valve is closed. Okay, then this delivery valve is closed, and this delivery valve is open. Okay, now you can see here, when my piston moves either from 0 to 180 degree, I have a delivery stroke. Okay, even my piston moves from 180 degree to 360 degree, during that also I have one delivery stroke. In both the rotation, I got one delivery stroke and one suction stroke. So that is my double acting reciprocating pump. So this is the classification based on the use of piston side. The next classification is on the basis of number of cylinder. Number of cylinders. So according to this, I have single cylinder pump that you can see over here. So this is my single cylinder pump. Okay. The second one is the double cylinder pump. So for double cylinder, you can see this diagram. Okay. So a double cylinder or two, this is also called two throw pump. Double cylinder or two throw pump. Now it consists of two cylinders and that are connected to a same shaft. Okay, that are connected to a single shaft. So each cylinder has its own suction and delivery pipe. This is important over here. So in case of double cylinder pump, each cylinder has its own suction and delivery pipe. Each piston is connected by a crank. Now the crank is set at an angle which is 180 degree. You can see the crank position is set at an angle of 180 degree. So on one side, one crank is on this side, and the second crank is totally in the opposite side, that is this one. So that we call as set at an angle of 180 degree. Okay. So thus, when there is a suction stroke in one pump, when there is a suction stroke in one pump, the in the another pump there is a delivery stroke. Okay, in the another pump there is a delivery stroke. So accordingly, the crank is set like that. So in this way, so liquid is delivered to the delivery side during each stroke of the pump. During each stroke of the pump. So this we call as crank angle. Okay. Then next is my triple cylinder pump. So that I also called as three throw pump. Okay. So you can see that this diagram for three throw pump. Okay. So in this diagram, you can see we have three different cylinders. Each cylinder has its own suction and delivery pipe. Now here you can see the crank is set at an angle of 120 degree. So you can say for every 120 degree crank rotation, we got one delivery stroke. Okay, so for every 120 degree rotation of crank, we get one delivery stroke. So that's why in one cycle, we got three delivery stroke. Okay, so that's why this pump is called three throw pump. So this is triple cylinder pump. The next is the formula for discharge through reciprocating pump. The formula of discharge. Okay, so formula for discharge. So now you can see here, this is my single cylinder pump. So you can see here capital A, this is the area of cross section of the cylinder. Okay, so when my piston moves from extreme left, that is from this side, to extreme right, that is from this side. Okay, so I can mark here, this is my piston movement. Okay, so that piston movement I can represent by L. So this L is called stroke length. Okay, so if R is the radius of crank, so 2 times R is my stroke length. Okay, then N is speed of crank, that is in RPM. So now I can write the formula for discharge. So that is my QTH, theoretical discharge, that I can write as ALN divided by 60. So the discharge through pump per second is equal to the area into the stroke length into the RPM divided by 60. So this is the discharge through pump per second. So in this case, I neglect the thickness of piston rod. So this is my piston rod. Okay, so I neglect here the thickness of the piston rod. If I consider it, my effective area is total area of cylinder minus the area of piston rod. Okay, so from that side now, If you talk about discharge through this side now, so that discharge I can write as QTH is equal to area. Now the effective area is A minus AP. Okay, into L into N divided by 60. Okay, now if I talk about the discharge, total discharge during one cycle, so that discharge becomes QTH, discharge per second. I can write as ALN divided by 60 for double acting plus A minus AP LN divided by 60. So this is the formula for double acting reciprocating pump, and this is the formula for single acting. This is the formula for single acting reciprocating pump, and this is for double acting reciprocating pump. Okay. Now, if I neglect the area of piston rod, that is my this AP, so then I can write this discharge is approximately equal to, so discharge per second is approximately equal to 2ALN divided by 60. So the discharge of double acting reciprocating pump is twice that of single acting pump. Okay. So if there are some leakage loss and also there is some time delay in the closing of the valves, okay, there is some time delay in the closing of the valves. So there is my actual discharge. Okay, so that actual discharge is lesser than the theoretical discharge due to leakage and time delay of valves. Okay, so QA is actual discharge is less than the theoretical discharge. So now I can introduce one more term that is called slip. So slip is equal to theoretical discharge per second minus the actual discharge per second. And then the percentage slip. So QTH minus QA divided by QTH into 100. Okay. Then my coefficient of discharge, that is Q actual divided by Q theoretical. So this value of CD for reciprocating pump uh, lies between 0.95 to 0.98. Okay. And normally for a good condition pump, the percentage slip, that is 2%. So up to 2% of slip, percentage slip, we can say the pump is in good condition. Now, in case of reciprocating pump, it is not always possible, or you can say it is not always true, that my actual discharge is less than the theoretical discharge. So you can say, in case of reciprocating pump, we have negative slip also. So when there is a negative slip, when my QA is greater than QTH. So that means the actual discharge is more than the theoretical discharge. Okay. Now, when this happens, so this happens when I have a reciprocating pump with long suction pipe, short delivery pipe, okay, and pump is running at high speed. Okay, so at that very time, inertia force playing an important role. So the inertia force in the suction pipe becomes large as compared to the pressure force on the outside of the delivery valve. Okay, I repeat it. The inertia force in the suction pipe becomes large as compared to the pressure force on the outside of the delivery valve. So now this, due to this, my delivery valve opens before the piston has not completed its suction stroke. So during the suction stroke, due to inertia force of water, my delivery valve opens. So due to that, into the suction pipe, the excess amount of water goes. Okay, so that you can say some of the water is pushed into the delivery pipe before the actual delivery stroke started. So this way, the actual discharge becomes more than the theoretical discharge. Or you can say, when this happens, my CD is now greater than 1 and slip becomes negative. Slip becomes negative. Okay. Then the formula for power input to the pump. So that formula I can write as the theoretical work done by the pump, that I can write as W, or W I can write as rho G into QTH into HSD, static head. So this is the formula for single acting reciprocating pump. So my HSD, I can write it as suction head plus delivery head. Okay, and this formula I can again write as rho G. Now my QTH for single acting pump is ALN divided by 60, okay, into HS plus HD. Okay, so that is my, so this is the work done by the pump, or you can also write this is equal to the power input to the pump. Power input to the pump, that is rho G ALN divided by 60 into HS plus HD. Okay. However, due to leakage or friction losses, the actual power will be more than the theoretical one. This is the theoretical power. So if eta be the efficiency of the pump, so I can write the actual power input to the pump is 1 upon eta into rho G ALN divided by 60 into G HS plus HD. Okay, so this is the formula for actual power input to the reciprocating pump. The next is the indicator diagram. Okay, now this diagram is the graphical representation between pressure head in the cylinder and the volume swept by the piston for one complete revolution or cycle. Okay, so you can say the indicator diagram is the graphical representation between the pressure head in the cylinder and the volume swept by the piston for one complete revolution or this cycle, one complete cycle. This swept volume you can see. Now this swept volume is A into stroke length, area of the cylinder multiplied by the stroke length. Now for the given cylinder, you can see that this volume swept is proportional to the stroke length. Okay, or you can also say the indicator diagram we can draw as, on one side we have the pressure head and on other side I have the stroke length. So a graphical diagram between these two we can also say as the indicator diagram. Now again that diagram is for one cycle or one complete revolution of the crank. Okay. Now if you see single acting reciprocating pump, so in that I have a piston cylinder arrangement. Okay. So here I have the delivery pipe and here I have the suction pipe. So this is my sump. Okay. Now during suction stroke, you can see So what happened during suction stroke? Piston moves from right to left, sorry, from left to right. Okay. So my suction valve is open, delivery valve is closed. Okay. So at that very time, the water comes from sump to the cylinder. Okay. Now this water comes from sump to the cylinder only when the pressure generated inside the cylinder is less than the atmospheric pressure. Okay. So pressure during suction stroke is lesser than the atmospheric pressure, and that is by an amount HS meter of water. That HS is my this height from center to the sump level. Okay. So during suction stroke, you can say I have the pressure less than atmospheric pressure, and that is by an amount HS meter of water. Okay. So then during delivery stroke, my piston moves from right to left. Okay. And that very time, my suction valve is closed, delivery valve is open. Okay. At that very time now, I have to push the water from the cylinder to the required height through delivery pipe. So you can say at that very time, the pressure is more than the atmospheric pressure, that is by an amount HD meter of water. Okay. So if now I try to draw this indicator diagram, so you can see here along y-axis I have pressure head, along x-axis I have stroke length, and this is my atmospheric pressure. So you can say this is the head, pressure head corresponding to atmospheric pressure, and that is my HATM. Okay. Now during suction stroke, the pressure becomes, so I start from here. During suction stroke, pressure is less than atmospheric, that is by an amount HS meter of water, and that remains same during the suction stroke. So this is my stroke length L. So my crank rotation is from 0 degree to 180 degree. So at the mid, my theta is 90 degree. Okay. So at 180 degree position of crank, my delivery valve opens. Now piston applies the pressure on the liquid inside the cylinder. So at that very time, the pressure is more than atmospheric. Okay. So that pressure becomes now. So this is HD. Okay. And remains constant throughout. Okay. So now again, I say my crank rotation is from 0 degree to 180 degree, and in between theta is equal to 90 degree. Okay, so this is my suction stroke, and this is the delivery stroke. So at the end of the delivery stroke, my suction valve, my delivery valve closes, suction valve opens, and now again the pressure drop to atmosphere. Okay, then with the opening of suction valve and piston starts moving from left to right, the pressure drops to less than atmospheric pressure. Okay, so this completes my indicator diagram. So you can see here, I start from A. Okay, so A to B, you can see that is the uh, pressure head corresponding to atmospheric pressure. Then CD line for suction stroke, and EF line for delivery stroke. Okay, so this is my ideal indicator diagram. Okay, now you can see the work done by the pump per second. WQH, or I can write as rho G Q TH into HST, or this I can write as rho G ALN divided by 60 into HS plus HD. So this I can write as uh, rho G AN divided by 60, then into L into HS in plus HD. Okay. Now when my pump runs at a constant speed and for given area of cylinder, this term is constant. So I can write it as K L HS plus HD. Okay. Now I can say that work done per second is proportional to L into HS plus HD. Okay. So this is my area under indicator diagram. Okay. So you can see here, this is the side L. Okay. And this is the side HS plus HD. So work done is proportional to area under indicator diagram. So now you can say simply uh, my diagram CDFE, CDFE, that is my indicator diagram, indicates the work done by the pump, done per second by the pump if I draw that diagram on a particular scale. Okay. Now this indicator diagram we just discussed here has not taken into consideration the effect of friction in the pipe. Okay. And also the effect of acceleration of piston. Okay. So we neglect these two effects on the indicator diagram. So that's why I call that diagram as a ideal indicator diagram. Okay. So if I try to introduce these effects separately, then I have a different shape of indicator diagrams.